Hidden behind the scenes of hospitals, food factories, scientific laboratories, and even theatrical stages, there exists a material that behaves unlike anything else in our daily lives. A substance so cold that it can freeze fruit in an instant, yet so elusive that it vanishes without ever turning into liquid water. This is dry ice, solid carbon dioxide. In the next chapter of our journey, we will trace the path of this remarkable substance, from its origins deep within industrial processes to its transformation into the icy blocks used to preserve, to transport, to clean, and to amaze. Join us as we follow the extraordinary journey of CO₂, from gas to snow to the dry ice that powers essential systems all around the globe. Dry ice stands apart from almost every other material known to industry. The key to its uniqueness lies in a physical process rarely encountered in the world around us: sublimation. Unlike ordinary ice, which melts from solid to liquid, dry ice bypasses the liquid phase entirely. It transitions directly from solid to gas. No moisture, no melting, no residue, only a cold vapor drifting away. At 78.5 degrees Celsius, or 109 degrees Fahrenheit, dry ice creates a temperature so low that it can temporarily halt biological activity, preserve delicate samples, and rapidly reduce the temperature of nearby materials. This extraordinary cold, combined with the complete absence of water, makes dry ice indispensable in many fields. In medicine, where ultra-low temperatures are needed to transport vaccines or biological specimens. In the food industry, where freshly frozen products must remain cold during long journeys. In research laboratories, which rely on stable cooling for experiments. In industry, where dry ice blasting cleans machinery without chemicals. And in the world of performance and entertainment, where its thick white fog has become iconic. To appreciate the role of dry ice in modern society, we must first understand where its primary component, carbon dioxide, comes from. Contrary to what we might imagine, carbon dioxide is almost never produced specifically for dry ice. Instead, it is captured from existing industrial activities where it already appears as a byproduct. One of the purest sources comes from breweries and distilleries. During fermentation, the very process that transforms sugars into alcohol, large quantities of CO₂ naturally bubble out of the tanks. Rather than letting this gas escape into the atmosphere, it is collected and directed toward purification systems. Another major source lies in ammonia production, a cornerstone of modern agriculture. The Haber-Bosch process, responsible for creating fertilizers, generates CO₂ in significant amounts. This gas, too, is captured before it can disperse into the environment. In petrochemical plants and refineries, hydrocarbons undergo transformations to become fuels or chemical components. These operations also produce carbon dioxide that can be recovered. Even power plants where fossil fuels are burned to generate electricity produce CO₂ that can be captured, though here the purification steps must be more extensive. Wherever it comes from, the captured gas cannot be used immediately. It must be purified, dried, compressed, and cooled before taking part in the creation of dry ice. Raw carbon dioxide carries with it traces of the processes that created it. It may contain dust or particles, remnants of hydrocarbons, moisture, or other gases. To transform CO₂ into a usable material, it undergoes a succession of purification steps. Filters remove large particles. Chemical scrubbers wash away contaminants. Drying systems extract water vapor. Purification columns finish the job by pushing the gas toward levels of purity exceeding 99%. Only then can the CO₂ be compressed, up to around 15 bar, and cooled. Under this combination of high pressure and low temperature, it becomes a liquid. This transformation is essential. Liquid CO₂ is far easier to move, store, and control. It is collected in massive insulated tanks, capable of holding hundreds or even thousands of tons. Valves, gauges, insulation layers, and safety systems ensure that the pressure remains stable inside these reservoirs. From here, the liquid CO₂ will be directed toward the heart of the dry ice production units. Inside the dry ice factory, the liquid carbon dioxide begins its metamorphosis. The process starts when the liquid CO₂ is forced into a specialized chamber. There, it undergoes a sudden and controlled drop in pressure from about 15 bar to roughly 5. This abrupt depressurization causes a remarkable reaction. Part of the CO₂ instantly evaporates, pulling energy away from the remaining portion. As a result, the temperature plummets so rapidly that the remaining CO₂ solidifies on the spot. The product of this transformation is a fine powdery substance often called CO₂ snow. It resembles freshly fallen snow, light, soft, and intensely cold. But despite its appearance, this snow cannot be used as dry ice in its loose form. It must be compacted and shaped to give it stability and usable density. The journey continues toward the presses. Hydraulic presses exert immense force on the CO₂ snow, compressing it into solid, durable forms. The types of dry ice produced depend entirely on how the snow is shaped. Large blocks, sometimes weighing several kilograms, are compressed for long-distance shipping and long-duration cooling. Thinner slices, known as slabs, are created for catering, grocery distribution, and smaller storage needs. Perhaps the most versatile format is the pellet. Pellets are small, cylindrical pieces of dry ice widely used in logistics and industrial processes. Two pellet sizes dominate the market: 16-millimeter pellets used for refrigeration and transport, 3-millimeter micropellets used in dry ice blasting. To make these pellets, the CO₂ snow is pushed into an extruder equipped with steel plates perforated by holes of specific diameters. Under the pressure of pistons or screws, the snow is forced through the openings, forming cylindrical strands that are cut into uniform lengths. Once shaped, each piece of dry ice begins its short life, a life destined to sublime back into gas. Before the dry ice can leave the factory, it undergoes careful inspection. Technicians verify density, shape, weight, compaction, purity, and resistance to breakage. Only the batches that meet strict standards move forward. Dry ice is then packed into heavy insulated containers made of polystyrene or polyurethane. These containers are designed to slow sublimation, the natural evaporation of dry ice. Even under excellent insulation, dry ice may lose between 5 and 10% of its mass each day. For this reason, delivery is rapid. In many industries, dry ice is ordered, produced, and shipped all within the same 24-hour cycle. Although dry ice may seem exotic, its uses touch many aspects of modern society. In the medical world, it preserves vaccines, cools biological samples, and safeguards organs destined for transplantation. In the food and agricultural industries, it maintains the cold chain, freezes delicate ingredients, and allows fresh or frozen products to travel across continents. In industrial environments, dry ice pellets are used in blasting systems that clean machinery without chemicals, without water, and without damaging the underlying materials. In entertainment, dry ice plays a purely visual role. Its dense fog has become a familiar companion to theatrical performances, concerts, theme parks, and film productions. And in modern logistics, when electricity is unavailable or unreliable, insulated containers filled with dry ice keep meal kits, research samples, and frozen goods safely chilled during transport. Dry ice is everywhere, yet often invisible. Dry ice is a material of contrast. It is harshly cold, yet gentle enough to handle delicate specimens. It is solid, yet destined to vanish. It is created through advanced industrial processes, yet it evokes a sense of natural wonder. From its journey as captured CO₂ to its transformation into snow, blocks, and pellets, dry ice reminds us how much of our modern world depends on precise scientific and industrial mastery. So the next time you see a drifting cloud of white fog at a concert, or receive a frozen package in the heat of summer, or watch laboratory samples being transported across the globe, remember the long and meticulous journey behind that cold, silent material known as dry ice.